So the first thing I want to start with here before we go on to Chapter 17 is I've got your project pulled up. And we talked about number 1, we talked about number 2 and number 3 on Tuesday. I'd like to have say a few words about number 4 here. Number 4, that's the regression problem, where you're going to make a scatter plot, you're going to find the least squares regression line, and so on and so forth. Problem 4 says, on the survey, questions 7 and 8 ask students to give an estimate of how much they spent on books for school this semester and how many credit hours they are taking this semester. So you got 2 quantitative variables, right? How much they spent on books and how many credit hours you're taking. We are interested in seeing whether we can use the students' credit hours to predict how much they will spend on books for the school for the semester in U.S. dollars. Now, you see that word predict? That means we're treating one of these as an explanatory and the other as a response. The variable that you're using to make the prediction, right? Can we use the students' credit hours, explanatory variable, to predict how much they will spend on books is your response variable. Now, remember, that makes a difference when you make a scatter plot, when you do the regression line, that you've called one the explanatory and you've called the other response. Again, explanatory is the credit hours, and the response is how much they spend on books. It says, create an appropriate display to display a graph to display the relationship between hours and books. Well, I also got Minitab up here, and there's the file. What kind of graph do I want to make to show the relationship between 2 quantitative variables? That's a scatter plot, right? We choose scatter plot. We just want a simple one. I don't want anything funky here. What's the y? The y is always a response. What was my response going to be? How much you're going to spend on books? What was the explanatory? What do we think was going to help predict that? Credit hours. We click OK. There's your graph. Yeah, I mean, it don't look like the ones we had in the book, but you got to remember, there's a lot of people taking the same number of hours, right? You see that they paid different amount of money for their books, but you see there's a lot of people taking like 15, 10, 12, whatever it is. There's a lot of people taking the same thing. There's your graph. Does this plot show a positive association, a negative association, or no association? You see lower left or upper right? That's your positive association, right? Explain what this means with respect to the variables being studied. Yeah, I know you can see that's the lower left to the upper right. Hell, that's a positive association. What does that positive association mean? That means the more credit hours you took, the more you spend on books. The fewer credit hours you took, the less amount of money you spend on the books. That's what they're asking you here for. Okay? Describe the form of the relationship between hours and books. Damn. Look halfway linear? Remember, that's what we're always checking for. I see it linear, but I got a little curve in it there, don't I? Yeah, it looks linear with a little bit of a curve. Report the value of the correlation between this pair of variables. In other words, find R. I'm going to leave this guy up here, but I'm going to slide him over. Where you find the correlation is you go to Stat, Basic Statistics, Correlation. What's your 2 variables? Books and hours. No need to do this, display the p-value. The correlation is 0.863. In other words, what that's telling you is you have a strong positive linear relationship, correct? That's a strong, right? We're close to 1. We're at 0.86. That's a strong positive linear relationship. Based on the information displayed in the graph and the correlation you just reported, how would you describe the strength? I'm not going to repeat myself. I just told you. Using Minitab, obtain the equation for the least squares regression line of books on hours. Copy and paste the output. Here's what I would like to see out of you. I'm going to get rid of this scatter plot. Now, I'm going to do it like this because this is the only place I did this. Regression, fitted line plot. Right? That's where I showed you to get your least squares regression line. What's the response? The response is how much you spend on books. The predictor, your explanatory, is the number of hours. That's what I'm expecting you to cut and paste. That whole thing, scatter plot and all, because the regression line's at the top of that, right? It says books is equal to minus 518.1 plus 63.63 hours, right? That's what you want there. Take that whole thing and give it to me. It put the line on there and everything for you. Then it says interpret the value of the slope. Let me ask you this. Which one of those numbers is the slope? The minus 518.1 or the 63.63? It's the 63.63, right? And what's the slope always tell us? What do we always think about? Well, if you increase the number of credit hours by 1, how much more are you expecting to pay? $63.63 on average, correct? Remember, you increase the explanatory variable by 1 unit, 1 credit hour here, then the response variable, the amount you spend on books, is going to increase because the slope is positive. It increases by the slope. For each additional credit hour that you take, the amount of money you're going to spend on books increases by $63.63 on the average. That's your interpretation of the slope. Use a regression line or equation in part F to predict the cost of books for school for a semester for a student who takes 15 credit hours. Plug 15 in for credit hours. You'll get a cost, right? You'll plug 15 in there. Now, how well does a regression equation fit the data? You see that question there? They're asking you about R squared. Remember, R squared tells you how successful you were. Well, if you give me this here, then you can read R squared off the side there as 74.5. That's just 0.863 squared, right? So what this is telling me is 74.5% of the variation that we are seeing in the cost of the books is explained by the linear relationship. How well did we do at fitting a line? Remember, the closer that number gets to 100%, the better we did. Oh, the line fits the data rather well here. Okay? That's what they're asking you for. Explain. Justify your answer with appropriate plots and summary statistics. The summary statistic you want is R squared. It tells you how much of the variation, 74.5%. What kind of graph would you make to show this picture? Well, I'm going to X this out and go right back to where I was. Stat, regression, fitted line plot. All that stays the same. You didn't change the variables. The graphs, I would like the residuals, and I'd like the residuals versus your explanatory variable. Remember that residual plot that we talked about? I mean, that's been a long time ago. That was in Chapter 5. Okay? If I click OK. OK. There's your residual plot. How's it look? Well, it looks like I can see that little curve in there, right? But things aren't, the majority of the observations are not too far away from the zero residual, right? That's trying to confirm. R squared, 74.5%. We did a good job fitting the line. The residual plot is confirming that for you, right? It looks like, yeah, things are kind of close, okay? Maybe I shouldn't have did that whole problem for you. Remember, you're going to go back and look at the one from the spring, right? It'll tell you the exact language and what you want to say here. Now, we come down here, and I'm going to just pick one of these. There's a F that there's a number 5 for females, and there's a number 5 for males. What I'm interested in here is what graph do I make, and then how do I make this two-way table? I never showed you how to make a two-way table when you had the raw data. It says, question 3 from the survey asked students, do you think government should require mandated childhood vaccinations? And question 2 from the survey asked, what is your age? Okay. The variable age has been split into 2 groups, 16 to 21 and, what is it? Over 21, right? So they made the categorical variable out of your age, right? You were either 16 to 21 or you were over 21. And then I'm assuming you answered yes or no to this, do you think the government should require mandated childhood vaccinations? Okay. It says we want to check if there's a relationship between child and age group. In other words, what you said about mandatory vaccinations and your age. Okay? Assume that the students who took the fall 2015 survey are an SRS from the ETSU students. It says create an appropriate graph to display the relationship between child and age group. Insert your graph here. Everybody understand you got 2 categorical variables? So this is going to be some kind of cluster graph or some kind of stacked segmented bar graph. It's going to be one of those 2. This is a problem out of Chapter 6 in your book. Now, here's the way I would attack this problem if I was doing it. I think, for some strange reason, I think your age group that you're in might help explain how you feel about mandatory vaccinations for children. So I'm going to treat your age group as the explanatory variable and the what they said about the childhood of vaccinations as your response variable. So that means I'm going to want particular conditional distributions here, right? Remember, it's always the conditional distributions of your response variable for the given values of your explanatory variable. So here I'm going to have two conditional distributions of, what's the variable here? Child, given the two different age groups. Okay? So if I come over here and I'm going to make a graph, and I want a bar graph. Now, here's the warning. Every time we made a bar graph in this class, on that drop-down menu where it says the bars represent, we always change that to values from a table, right? No, you got the raw data here. So you've got counts of unique values. You've got everybody listed, and you've got everybody's value for the both variables here. So I'm going to leave that alone. This is the only time I didn't change this. And number one, I didn't change that either. So I'm going to do the cluster. You can do the stack, the segmented one. I'm going to do the cluster. I want to click OK. Now, whichever variable you put in first, that's the given that part. So I'm going to put in, now be careful here. You see there's a variable in column 3 called your age, and you see there's a variable down here in column 16 called your age group. If you put column 3 in there, you're going to get some screwed up looking answers. Right? So we need to put in the age group. And then we're going to put in child, right? That must have been the variable. So this is going to give me the two conditional distributions of child, what they said about child mandatory vaccinations, given the two age groups, hopefully, if I did this right. One other thing I ask out of you at this point is go to chart options, show y as a percent. We need to be looking at percents here. And show y as a percent, and then you want it within categories at that level. In other words, I want to see two conditional distributions with these two separate bar graphs I'm going to have. Okay? If I click OK, I click OK. I have two conditional distributions of what they said about child vaccinations given the different age groups. I got one for 16 to 21, and I got one for over 21. That's the graph you want here. If you do the stacked or the segmented, they'll be on top of each other. You set everything up exactly the same way. That's your graph. Now, I'm going to leave that there for a second, and I'm going to come back here. Part B says create an appropriate two-way table to summarize the data and insert it here. Okay? I come back here. I've never made a two-way table for you. I'm going to go to Stat, Tables. That's to make a two-way table, you go to Stat, Tables, and then there's something called cross-tabulation. You're going to categorize by both of the variables is what you're going to do. Okay? So I'm going to choose Stat, Tables, cross-tabulation. The rows, now look, I know there's a drop-down menu up here. You've got the raw data. You don't have to mess with that. For the rows, just for me, I'm going to put the variable child. And for the columns, I'm going to put the age group. Okay? That's all I got to do is put my... Look, you could put either one in. It makes no difference. You're going to get the same thing. Except the rows and the columns will be flip-flopped. Makes no difference. All right? If I click OK, there's your two-way table. That's just like the two-way tables out of the book, right? Notice the column variable is the age group. The row variable is what they said about mandatory vaccinations of children. Yep. It looks to me like there's 814 people in this table. Yep. That's the bottom right-hand corner. It looks to me like 120 of them were 16 to 21 and said no. It looks like 540 of them were 16 to 21 and said yes. I'm reading the numbers off the table. Copy that. Where I started? Stat, tables, cross-tabulation. Put one variable in as the rows. I put child. Put the other variable in as the columns. And I click OK. Cool? All right? Now, you highlight this because that's the only way you can copy and paste anything from here. All right? So I would highlight it, copy and paste. Okay? Put it over there. Then, when I come back here, there's a part C, a D, an E, and an F. These are 4 probability questions where you're going to select one of these students at random. Part C says, what's the probability the student is over 21 and favors government-mandated childhood vaccinations? You want both of those characteristics. There's no given that. You want both of them. You want they're over 21 and they favor government-mandated childhood vaccinations. You're going to divide by 814 here. All right? Then there's Part D. What's the probability that the student is either over 21 or favors government-mandated childhood vaccinations? In other words, you want over 21 or they said yes. Remember, you're going to look at the ones that said 21, the ones that said yes, and you're going to subtract out the ones that said both because you counted those twice. And you're still going to divide by 814. Part E. What's the probability that this student is age 16 to 21, given that the student opposes government-mandated childhood vaccinations? You want to know what's the probability that the student is 16 to 21, given that they said no. You're only going to look at the ones that said no. Part F. What's the probability that this student opposes government-mandated childhood vaccinations, given that they are age 16 to 21? You want the probability they said no, given that they are 16 to 21. You're only going to look at the ones that are 16 to 21 here, and you're going to look at the ones that said no. Out of the total that were 16 to 21. Those two are just the opposite of each other, right? Look at them. One is 16 to 21, given that they said no. The other one is no, given that they were 16 to 21. Now, I got to look at Part G. Do you think that there may be an association between age group and child? Why or why not? Explain your reasoning based on what you see in your graph. This is where I was asking you before. We got 2 categorical variables here. We're wanting to know if they're related or not. Does it make a difference? This is what I want to know. I'm going to put it to you like this. Here, what I want to know is, does it make a difference, your age? Does your age tell you anything about what you were going to say about these mandatory vaccinations? What I'm asking you is you're looking at these 2 conditional distributions, these 2 bar graphs here that are one for 16 to 21 and one for over 21. Do they look the same or do they look different? They look very similar. Right? They look very similar. Without doing anything else, if I had to look at this and say, yeah, here's what I can see. The over 21, there was a little higher percent that said no, right? The under 21, the 16 to 21, there's a little higher percent that said yes. But the overall, they're real close to each other. So what I want to know is based off what you're seeing there, did the age group make a difference on how that people felt about mandatory vaccinations? And here, it looks like there's a slight difference. I don't know if it's enough that I want to say anything about it. They look very similar to me. Okay? Now, I know I'm wasting time here for you. I understand that. But that one was for the females, right? So I can't leave you gentlemen out. I just feel compelled. So this is the one the males are going to do. Military and welfare. This ought to be good. Question 4 from the fall survey asks, should military personnel be armed in military buildings on United States soil? I'm guessing you must have answered yes or no. Question 5 from the survey asks, should those on welfare be required to pass a drug test? Can you imagine we got those 2 questions in the same problem here? Now you understand that answer was yes or no also, and you got 2 categorical variables again just like you did in the previous part, right? It says, we want to check if there's a relationship between military and welfare among ETSU students, assume the students that are in SRS, and so on. Create an appropriate graph. This is the same problem we just worked, right? Except now it's military and welfare. Now, look, in both of these problems, you could have went either way. But for some reason here with this problem, when I was looking at this earlier, I was thinking, and I don't know why I was thinking this, I was thinking, if he was in the military, yes or no, that might help explain your little thought about the welfare folks. In other words, I'm going to treat, just for the sake of things here, I'm not saying you can't go the other way, but for me, I was just thinking that I would treat the military variable as your explanatory variable and the welfare one as your response. I mean, I guess we could have flip-flopped it, and maybe your thoughts about welfare would tell me whether you was in the military or not. That seems like a halfway reasonable thing, too. But I'm going to treat military as the explanatory variable and the welfare as a response. So when I come over here, I'm going to do the same thing to you. I'm going to go to graph, the bar chart. I'm going to give you the cluster one. You can do the other one. This time, what do I want to put in first? I want to put in military first and then welfare. So this is going to give me two conditional distributions of welfare given what you said about military service, right? Yes or no. Just to check, I want Y as a percent within categories at level 1. Okay, okay. So I have two conditional distributions. There's one for yes military service, no military service, and yes military service. Okay? We'll come back to this in a moment. I want to come here. I want to make you the two-way table. So I'm going to slide over here. I'm going to go to Stat, Tables, what was it? Cross Tabulation. For the rows, I'm going to put the welfare. And for the columns, I'm going to put the military. Look, I can't help it. If I got explanatory and response, I usually make the explanatory variable the columns, and I make the response. Nobody cares. We just want you to make the two-way table. Put one as the rows, and the other was the columns. Again, it looks like there's 814. 31 said no military and no to drug testing. 66 said no military and yes to drug testing. 68 said yes to military, no to drug testing, right? 649 said yes to military and yes to drug testing. Okay? Based off of that, then we're going to start asking you probability questions. Now, notice how similar these are to before. The first one's an and, right? They opposed to arming military people and said welfare should not require to pass a drug test. That's a no and a no, right? That's what you're looking at there. Okay? Part D is an or. What's the probability the student favors military personnel? That's a yes. Or those welfare should not require a drug test. That's a yes or a no, right? Yes on military, no on drug testing. E and F are given that. These are conditional probabilities. And then I get down here to G. Do you think there may be an association between military and welfare? Why or why not? Explain your reasoning based on what you see in the graph. Those two look different to you? Oh, yeah, there's something up here. What's up? If you said military, you're more likely to want drug testing, yes? See, there's way more in the ones that said yes to military that said yes to drug testing for welfare. See the ones that said no military? The bars aren't as tall, right? That makes sense? The previous one about age group and what you think about child vaccinations, they were very, very similar. These are not very, very similar. See how one's real tall, one's real short over here, and then one's not? Yeah, there's something up here. There is definitely a relationship between military service and whether you think that people getting welfare should be drug tested. Okay? And the relationship is, if you're in the military, you're pretty sure they should be drug tested. If you weren't in the military, you're thinking, nah. In the military? Yeah. That's the real tall one over there on the right. Okay? Now, where does that take us? Now, you know everything I just did was videotaped, right? So you want to see exactly what I did? It's there. That brings us to problem 6. We can't do that yet. Right, we need some more of this inference to be able to do that. When we can do this, I'll come back and tell you. And then the only other thing you got left is the bonus problem. And I need some more inference to be able to do that. When we can do it, I'll tell you. All right? So, I mean, that gives you something to work on over the weekend. That's the reason I didn't give you any homework. I mean, you can do the first five on the gateway. I figured that was fair, right? Look, the reason I pull this up and we talk about it is because you realize I just got to review like 3 or 4 chapters there with you about two-way tables, the cluster graphs, regression. We got a real quick review there. Okay? Now, what we're going to work on tonight, and I don't think we'll get through it all, is this chapter 17. Okay, we're doing statistical inference. The first piece of inference we know about is confidence intervals. That's what we did on Tuesday. And I told you on Tuesday a confidence interval is used to estimate a population parameter, right? You got an estimate plus or minus a margin of error, and we form that interval. Well, then there's chapter 17. And chapter 17 is tests of significance. This is your second inference method. And again, they talk about the basics. All right, so it's our beginning here. Now, one morning, on Tuesday, when we started chapter 16, I gave you 3 simple conditions that needed to be met. Well, they needed to be met in chapter 16, and they need to be met here. You always need a simple random sample. The population distribution that you're choosing from needs to be normal. The third one is, somewhere in the problem, they got to give me sigma. They got to give me the standard deviation of the population. Those 3 still hold here. Even though I'm not going to write them down, those are 3 simple conditions that have to be accounted for in chapter 16 and chapter 17. Now, the goal of a test of significance, all right? Just like the goal of a confidence interval is to estimate a population parameter, in our case to estimate mu, the goal of a test of significance is to assess the evidence provided by the data. I'm going to put in parentheses here, the data comes from your sample, right? About some claim for a population parameter. I underline the word evidence for a reason here. That's how I know they're asking for a test of significance. Now, before I make up my own little example here, okay? The thing about a test of significance, again, just like the confidence interval is based off the sampling distribution of a statistic, the test of significance is based off the sampling distribution of a statistic. All right? The catch about the test of significance is it has a very elaborate vocabulary. And it's not just a one-step thing. It's not like just calculating the confidence interval. There's probably 4, possibly 5 steps to a test of significance. I'm going to give you my example, and then we're going to back up, and we're going to look at each step by itself. Okay? So what I want to do is this. I'm going to give you an example that I think we can all follow for a test of significance. All right? And it's got nothing to do with means or anything like this. Here's my claim. And my claim is real close to, what I'm going to talk about is real close to this example 17.1, but I'm going to up my numbers just a tad. Let's say I'm a basketball player. Been a while, but let's say I was a basketball player. I claim that I make 80% of all the foul shots I'm going to take. That's pretty damn good, right? 80%. So I've just made a claim about some kind of population parameter. What percentage I'm going to make when, no matter how many I shoot, I claim I'm going to make 80%. So I just made a claim about a population parameter. But you all look at me and you go, dude, you look kind of old. I think we should go downstairs to the gym and I think you should shoot 20 just to see what you can do. Right? You never trust anybody at their word. Hell, you test them. Yeah? So you take me downstairs. You make me shoot 20 of them. I got a question for you. If I'm going to go downstairs and I'm making this big claim that I make 80% of them and I shoot 20, how many of you expected me to make? You're expecting me to make 80% of them, right? You're expecting me to make 16, yeah? Everybody agree? If it's really true that I make 80% and I shoot 20 of them, you're expecting me to make 16 of them. Let's say we go downstairs and I make 15. How do you feel about my 80%? Shit. That's just in the averages. If I make 17, how do you feel? What about 14? That's pretty close to the 16, right? 13? Hell, 13 is not as good as 14, but you're still not far off. Hell, you're only 3 off from 16. What about if we go downstairs and I make 5? That's exactly what you do. Folks, in case you can't hear them, they're laughing at my ass. You're like, what? You claim what? You made 80%, we went downstairs, you shot 20, and you made 5? You don't believe me, right? So the further we get away from what you're expecting to happen, the more likely you are not to believe that I make 80%. Agreed? Right? I picked 5 for a reason, because I knew if I told you 5, hell, 5, you're expecting 16, you made 5? Ain't no way. There's no way you make 80%, right? We're expecting you to make something close to 16. You made 5. So what do you believe, other than I'm a liar? You don't believe I make 80%. What do you believe? I actually make less than 80%. Agreed? What I just described to you, that's a test of significance, without all the calculations and all the fancy words. Okay? We make a claim. We test it by taking a sample. Me going downstairs and shooting 20 of them, that's your sample. See what happens. You know what you're expecting to have happen. You're expecting me to make 80% of those. You're expecting me to make 16. I made 5. Dude, there ain't no way you made 5. That's very unlikely to happen if you really make 80%. If we're really expecting you to make 16, you make 5? Nuh-uh, something's wrong. You don't make 80%. Maybe you make 50%. Maybe you make 40%. Something closer to the 5 you actually saw. That's a test of significance. That's without all the elaborate vocabulary, me calculating anything. That's the thought. You know what else is a test of significance? You know this one too. Anybody know anything about a jury trial? Right? In a jury trial, you know, where the guy's on trial for his life. What's the judge say to start with? This guy's innocent until proven guilty. We just make a claim about the guy? The defendant? It doesn't have to be a guy. Did we make a claim about him? I know there's no numbers. It don't look like a stats thing, but a jury trial is a test of significance. The judge says, this person is innocent until proven guilty. Then what happens? The lawyers start giving you evidence, right? And once the evidence reaches beyond the reasonable doubt, what's the verdict come back? Guilty. Right? You changed it. Once you're so far away from what a reasonable, I can't remember all the words, what a reasonable person would assume, once you're so far away, look, in case you don't know, there's a reason why my hands are doing this. I got a number line here, and right here's what I'm assuming to be true, and the further I get away from that, the less likely you are to believe that. I believe something over here. In a jury trial, if you believe he's innocent, the further I get away from that, beyond a reasonable doubt, right, past that point, the guy's guilty. What happens if we're not past a reasonable doubt? The guy comes back, not guilty, right? Jury trial is a test of significance. Now, here's the way we're going to attack this. And I'm going to attack it the following, all right? I want to look at this example 17.2. And again, without all the fancy language, just something that actually fits with what we're doing. It says, Diet Colas use artificial sweeteners to avoid sugar. These sweeteners gradually lose their sweetness over time. Manufacturers therefore test new colas for loss of sweetness before marketing them. Trained tasters sip the cola along with drinks of standard sweetness and score the cola on a sweetness scale of 1 to 10. The higher the score, the sweeter it is, with larger scores corresponding to greater sweetness. The cola is then stored for a month at high temperature to imitate the effect of 4 months storage at room temperature. Each taster scores the cola again after storage. This is a matched pairs experiment. Our data are the differences. The scores before minus the scores after. That's your data, right? It's matched pairs. It's a before and after. They scored it before, they let it high temperature for a month, they tasted it again, they scored it again. You might have gave it a 6 and you might have gave it a 4. So the value we're going to see out of you is a 2. Okay? It says, suppose we know that for any cola, the sweetness loss scores vary from taster to taster according to a normal distribution, the population distribution is normal, with a standard deviation, sigma is equal to 1. Anybody know why they're given these two? That's part of your simple conditions, right? The population distribution is normal, the standard deviation is 1 here. The mean mu for all tasters measures loss of sweetness and is different for different colas. So mu is the mean loss of sweetness, where we take the average over everybody. If we could do the before and after with everyone. Here are the sweetness losses for a cola currently on the market as measured by 10 trained tasters. Here's your sample. Your sample size here is n is equal to 10. It says the mean of these 10 differences is x bar is equal to 0.3. Okay? They added those up, right? The sign being involved. Look, if you look at the first person there, their difference is 1.6. What do they think happened to the cola over time? It lost sweetness, right? They scored it higher before than they did after. Remember, you subtracted the after from the before. What's the fourth person think happened? A minus. How do they get a minus number here? Hell, they thought the cola actually gained sweetness after being sitting in the room with a high temperature for a month. They scored it higher after than they did before, right? Remember, it's always the before minus the after here. So it says that, right? So that on average, the tasters found a small loss of sweetness. You understand that x bar being positive, if this number is positive here, right, it loses sweetness. They scored it higher before than they did after, right? That's how I get a positive number. If they scored it higher after than they did before, they think it gained sweetness. What about if that was 0? What did they think happened? It never changed sweetness. They scored it a 6 and a 6, or a 4 and a 4, right? It never changed. It says, also, more than half, 6 of the tasters found a loss of sweetness. Those are the positive ones. 4 of them must have been negative. They think it gained sweetness. Are these data good evidence that the cola lost sweetness? Now, let me tell you what the magic word is in the question there. The magic word is evidence. See that, what I underlined in red? Evidence. They want to know if all this information here, this sample, this 10 trained tasters, is that evidence that the cola lost sweetness over that month of storage. Okay. Here's the way the test starts. We make a claim. And in this case, it's going to be, we're going to make a claim about mu. That's a population parameter. That's the mean loss for this cola for all tasters, anybody that would ever drink it. And ask, now here's the screwed up part. If the data go away. If the data give evidence against it, so we make a claim about mu, and then we're looking at the data, and we want to know, does the data give me evidence against that? I know, and I understand. We've been together quite a few weeks now, and every time I take any problem, whether it's an exercise or whatever, I always attack it straight on and do it, right? Whatever it is. Think about all those problems I just did off the project. It's always straight ahead. A test of significance, not so straight ahead. There's that little twist right there that I have written that we're going to make a claim and see if we get evidence against it. Think about me shooting my foul shots. I was going to make 80%. We went down there, right? We were looking for evidence against it, right? That's what we were doing. Okay? Now, here's the way this is going to work. We seek, in the question here, we seek evidence that the cola lost sweetness. Now, how do I know that's what I seek? I'm coming back to the thing. Are these data good evidence that the cola lost sweetness? That's what we're looking for evidence for. We want to know if this data is good evidence of that. Look, the one you're always seeking evidence for is always the one in the question. We seek evidence that the cola lost sweetness. Now, if the cola loses sweetness, remember, that means people would score it higher before than they did after. We would expect mu to be greater than 0. So I've taken the question and I've turned it into this mu, right? Mu is greater than 0 here. So if the cola has lost sweetness, we would have mu would be greater than 0. Mu would be positive. Okay? Now, I can't attack the problem straight ahead. So the claim, and this is the right language here, the claim we test, is no loss of sweetness. That means if there's no loss of sweetness, it tasted the same. It never changed after storage. If you scored it a 6, you would have scored it a 6. If you scored it a 3, you would have scored it a 3. That is mu is equal to 0, right? People would have scored it the same. Now, the statisticians in my department get excited when I stand here and tell the students, the reason we do things the why we do them is because that claim that we test, that we assume to be true, is mu is equal to something. I need that equal sign to get me started here. Okay? So now here's how it goes. If you'll give me all this, you'll notice there's 2 claims I have on that page. There's one we're seeking evidence for. There's the one that we are going to test. You see that one on the bottom? That's the one we're looking for evidence against. Now, I'm going to say that one more time. The one on the top was in the question. That's the question, right? We seek evidence. We want to know, do we have good evidence of a loss of sweetness that mu is greater than 0? I can't attack the problem. Because mu being greater than 0, hell, mu could be 1, mu could be 1.7, mu could be 1.2, 7.8. Hell, I don't know, right? I can't do that. And so the claim we actually work with, that we test, that we assume to be true is no loss of sweetness. Nothing happened. There was no change. That mu was equal to 0. Okay? If that's the case, then I'm going to give you a couple of number 1, number 2, and so on and so forth. Number 1, if mu is equal to 0. What I'm telling you is we assume mu is equal to 0. That's what it means if mu is equal to 0. We're going to assume that there's no loss of sweetness with this particular cola that we're looking at here. That mu was equal to 0. If that's the case, then the sampling distribution, we're back to that guy, of x bar, remember x bar is your statistic here, is normal. Population distribution is normal. The sampling distribution is normal. The mean is, how do I know the mean 0? What's that shit at the top of the page? Mu is equal to 0. That's your mu, right? We're assuming this to be 0. And then what's the standard deviation? It's the standard deviation of the population. Sigma's 1 over the square root of your sample size. Now, I'm going to put this in blue. It's normal with a mean mu, standard deviation sigma over the square root of n. We've assumed mu to be 0. The standard deviation was given to me to be 1. The sample size we were looking at here is 10. If you pull the calculator out, you're going to get this. It's normal, the mean is 0, and you get a 0.316 there. Yeah, I'm going slow. I'm in no rush at this point. Because if I get you to understand this one, all the rest of them work exactly the same. It's just pulling the shit out of the problem. Now, here's the thing. All right? The claim we just assumed to be true, that mu is equal to 0, you know what we just did? We're making a claim about where that sampling distribution is centered. Remember? It's centered at its mean, right? We're telling you it's centered at 0. That's what we're doing. Anytime I do a test of significance here, it's always going to be a claim that mu is equal to something. So I'm making a claim about where that sampling distribution is centered. Yeah, the standard deviation tells me how tall the hump is and all that. I'm making a claim about where you're centered. Here I'm making the claim that it's centered at mu equals 0. That's what we're doing. Okay? So, number 2. Our x bar was 0.3. Right? Those 10 trained tasters, the x bar, the mean loss that they were seeing there was 0.3 over those 10. Okay? So here's what I have. I have this picture right here. Here's this normal distribution, mean 0, standard deviation 0.316, mu is equal to 0, and here sits 0.316. Excuse me, 0.3, my x bar. X bar is sitting right here at 0.3. I have a question for you. I'm always interested in how far the x bar is from the center. How far is 0.3 from the center? Is it very far? Here's the way you want to start thinking about it. Everybody see the standard deviation is 0.316? The standard deviation of that's 0.316. 0.3 is less than 1 standard deviation away. Is it very far away? No. It's not far away from the center at all. It's less than 1 standard deviation away. What do you know about the 68 part of the rule? Within 1 standard deviation, 68% of all the observations fall there, right? You have something that's very likely to happen if mu was equal to 0. You believe that? Right? X bar equals 0.3 is not far from mu equals 0. X bar equals 0.3 is very likely to happen if mu is equal to 0. I'm writing down the things I'm seeing here and I'm thinking. X bar equals 0.3, hell, it's less than 1 standard deviation away. X bar equals 0.3 is very likely to happen if mu is equal to 0. X bar equals 0.3 is not evidence against mu equals 0. No loss of sweetness. Remember, we're always looking for evidence against that claim that we're assuming to be true. In this case, we're looking to see if our x bar is providing us evidence against mu being 0. Mu equals 0 here, x bar is 0.3 here, you're not far away. That's very likely to happen. That's what you would expect to happen. You would expect an x bar being 0.3 if the mean was really at 0. Look, should I number these for us? All these are the same thoughts. Well, there's a number 4 while I'm here. X bar equals 0.3 is not evidence of a loss of sweetness. See, because if I had evidence against mu being 0, no loss of sweetness, then I would have evidence for a loss of sweetness. Since I don't have any evidence against no loss, I don't have any evidence for a loss of sweetness. Now you see that number 4? That answers your question that's in the problem here. Are these data good evidence that the cola lost sweetness in storage? And the answer is no. Now, you're going to see me talk to you. Every time I talk to you about test of significance, it's going to be the same way. You made a claim about where mu is equal. You just centered that sampling distribution. Where's your X bar? How far is your X bar away? X bar is 0.3. Hell, it's less than 1 standard deviation away. You didn't find anything. Okay? Now, here's what I want to do. There's an example, 17.3, and the only thing it changes, I want to give you the flip side of this. Here the sweetness loss is for a new cola. They changed the cola. New cola. Okay? Here they gave me X bar is 1.02. Everything else is exactly the same. Sigma's 1, N is equal to 10. We're looking at the same sampling distribution. You notice most scores are positive. We got bigger positive numbers. It says, are these data good evidence that the cola lost sweetness? Same question, different cola, different X bar, same sample size, same standard deviation, same sampling distribution. So when I look at it, here's my question. It's still normal. We're still going to assume that there's no loss of sweetness, that mu was equal to 0. The standard deviation is still 0.316. It's still 1 divided by the square root of 10. You still made a claim that mu was equal to 0 where that sampling distribution is centered. Now I got X bar is that a long way away? Okay, in relative numbers, 1.02 is not that far away from 0, right? How many standard deviations is it away? You see the standard deviation is 0.316. What's 3 times that? 0.948. That 1.02 is more than 3 standard deviations away from the mean. When you start getting something that's more than 3 standard deviations away, you are a long way away. Remember, 99.7% of all the observations fall 3 this way and 3 this way. You're looking at one of the 0.3% of all observations. Okay? 1. X bar equals 1.02 is far away from mu equals 0. 2. X bar equals 1.02 is very unlikely to happen if dude, you're looking at one more than 3 standard deviations away if mu is equal to 0. See, you actually did get the 1.02. So something has to be wrong with what's going on here. Number 3. X bar equals 1.02 is strong evidence against mu being 0. No loss of sweetness. So if we have strong evidence, and the only reason we have strong evidence is because X bar is 1.02 is so far away from the center, right? It's so far away from the center. It's so far away from what we assume to be true. We got strong evidence against mu being 0, no loss of sweetness. So what do we have strong evidence for? X bar equals 1.02 is strong evidence. For mu being greater than 0. Now, those are the same four on the previous page, except now that you have an X bar, it's a long way away. It's really unlikely to happen if you're really centered here. You're more than 3 away. Look, I'm going to come back up here for a second to this picture, because the picture tells me everything I want to know. X bar being 1.02 is more than 3 standard deviations to the right of the mean. Between 3 to the left and 3 to the right, there's 99.7% of all the samples will give you an X bar within 3 standard deviations of 0. 1.02 is not one of those 99.7%. It's one of the 0.3% that are on the outside. You understand that that's something that's unlikely to happen when its probability is less than 0.3%, right? That's very unlikely to happen by chance. In other words, something has to be wrong here. The X bar being 1.02 can't be wrong. Hell, they did the experiment and got X bar was 1.02. Well, what's wrong? You can't be centered here. You must be centered somewhere to the right. In other words, I'm trying to tell you, mu can't be 0, mu must be positive. Because if we pick that sampling distribution up and move it to the right, is that 1.02 so far out the tail now? No. That's what's going on here. Same problem, 2 different X bars. One X bar being 0.3, not far away. Likely to happen if mu was equal to 0. No evidence against no loss of sweetness. No evidence for loss of sweetness. 1.02, long way away. Very unlikely to happen if you're centered at 0. Strong evidence against no loss of sweetness. Strong evidence for a loss of sweetness. Okay, you want to go back to my foul shooting? Remember, I make 80%. You took me downstairs. If I make 15, which one of it is it? Which one does that correspond to? Is that the 0.3 or is that the 1.02 when I go downstairs and I make 15? That's the 0.3. You're not very far away from what you were expecting. Remember I told you 5? Which one does that correspond to? That's the 1.02. That's a long way away, and you didn't believe what I said. That's what I'm telling you here. Okay? Now, that's the story. Now, that's without all the... I still haven't given you the elaborate vocabulary. Okay, what kind of calculations are we going to do? I mean, surely the God you understand at this point, in number 1 in both of them, when I'm telling you that 1.02 is far away and 0.3 is not, what was I referring back to? I was referring back to a z-score, right? So you know a z-score is going to show up here. Yep. You see number 2? The one was very likely to happen. This one's very unlikely to happen. What the hell have we talked about in this class that tells you about how likely or unlikely something is to happen? There's going to be a probability calculated here. Right? That's what's going to happen. We're going to calculate a probability. And then 3 and 4, that's just based off of what we find out in numbers 1 and number 2. You know, what's your z-score here? How far are you away? What's this probability we're talking about where we're going to measure how likely or unlikely is something to happen? I mean, normally we don't give you both 3 and 4. Right? Because I gave it to you at 3 and 4 because I want you to know what we're doing here. Number 3 in both of them, I'm always looking for evidence against this claim that we assume to be true. And then number 4 is always what the question is about. Okay? Now, here's what we're going to do. We're going to take this, and we're going to go a step at a time. Now, I don't know if I give you a test of significance problem that you can work all 4 or 5 steps, but we can surely do the little pieces. Surely we can do the little pieces. So the first piece is stating hypotheses. These are claims that we're making. Remember, elaborate vocabulary. These are the statements of the claims with some notation and so on and so forth. Okay? So I'm going to do it like this. There's always two. There's something called the Null Hypothesis. I'm going to give you a list of things when I think about the Null Hypothesis. Everything I can think of here. This is the claim of no difference, no effect. Things are as it's the status quo. Nothing has changed. This is a claim that mu is equal to I put a question mark there because it's not always 0. It was 0 for this colas. Mu could be equal to some number. This is the claim about where that sampling distribution is centered. The null hypothesis is always mu is equal to some value. This is the one we seek evidence against. This is the one assume to be true in the problem we just did. The null hypothesis was no loss of sweetness, that mu was equal to 0. It's the one you seek evidence against. It's the one you assume to be true. It's a statement that mu is equal to something. It's this no difference, no effect. In other words, storing it had no effect on the sweetness of this cola. There was no difference between the before and the after. Okay? Now, that's the null. While we're here, it's denoted with the capital H for hypothesis and the little 0 for the null. And I read that, and I apologize up front. I don't normally read that H sub 0. The redneck in me comes out, and I read that H sub naught. You'll have to go back and look at some TV shows to see where that comes from. Yeah, when I read H, I read that H sub naught. That's H sub 0, right? That's the notation for the null hypothesis. So you won't see me write out that word now. You'll see H sub 0, right? H sub naught. That's the null hypothesis. Well, that's one claim. There's a second claim. See, if we find evidence against the null hypothesis, is what the test is set up to do. That's what we're looking for. If we find evidence against it, there's got to be something that we believe, right? So there's something called the alternative hypothesis. Okay. This is the one we seek evidence for. It's normally the one that's in the question. Okay? Now, the null is a claim that mu is equal to something. The alternative to that, we have some options here. There are three possibilities that we can have. There is a one-sided, I'm giving you the symbols that are going to show up. The alternative can be one-sided. You're only looking one direction. You're either looking to the left or you're looking to the right. That would be a one-sided alternative. And sometimes if I'm looking to the left, you'll hear me say it's a one-sided alternative to the left. Or it's a one-sided alternative to the right if I'm looking at greater than. Right? So I can have less than or greater than. Another possibility is a two-sided alternative. And what you'll see is you will be seeing not equal to. The alternative doesn't have the long list like the null does. The alternative is the one that shows up in the question we seek evidence for. You either got a one-sided or a two-sided. It's either less than, greater than, or not equal to. Now you understand, we're making claims about our population parameter here, right? These are all stated in terms of mu. The null stated in terms of mu. The alternative is stated in terms of mu. Never stated in terms of x bar. That's where your evidence comes from. And then, finally, it's denoted by a capital H subscripted with a little a. And I read that H sub a. That's your alternative. This is what you're seeking evidence for. It's the alternative to what the null says. Now, the problem we just did, this example, 17.2. The null, I'm going to give you the little template here. When you see me and I'm dealing with a population mean, we're making claims about a population mean, that's my template. The null is mu is equal to something, and the alternative is mu. We'll figure out whether it's less than, greater than, or not equal to something. Now, it doesn't make a difference which one you write down first. I just need them both. So the one about the loss of sweetness, the one I wrote down first was, the null was mu was 0. No loss of sweetness, no change, no difference, no effect. Whatever number goes there, goes there. The number is the same in both the alternative and the null. Now what we got to decide about is, okay, what was the alternative? What were we seeking evidence for? We were seeking evidence for a loss of sweetness. And I told you that meant mu was greater than. That's a one-sided alternative. You're only looking to the right. Now, I'm going to give you I'm going to come down here at the bottom. Always state the null, H sub naught, the alternative, H sub a, in terms of a population parameter. Always. Not your statistic that comes from the data. It's always in terms of your parameter. Now, here's what I want to do. I'm on the bottom of page 395. See, if I can't do anything else with the test of significance, surely the hell I can state these hypotheses. So I'm going to look at 17.3 here. It says, state the null and alternative hypothesis for the study of college seniors in the Philippines attitudes described in exercise 17.1. All right? So I'm over here to 17.1. I got student attitudes. Now, I'm going to have to read the whole problem before I can actually start stating the null and the alternative. It says, the Survey of Study Habits and Attitudes, the SSHA, is a psychological test that measures students' study habits and attitude towards school. The survey yields several scores, one of which measures students' attitudes towards studying. The mean student attitude score for college students is about 50. All right? And the standard deviation is about 15. A researcher in the Philippines is concerned at the declining performance of college graduates on professional licensure and board exams. She suspects that poor attitudes of students are partly responsible for the decline in the mean for college students who plan to take professional licensure or board exams is less than 50. Okay, so she gives this to SRS of 225, so on and so forth. Here's what I know. In this problem here, 17.3, I know they want me to state the null, and I know they want me to state the alternative. Now, nobody says good evidence. It's the wording. Look, the alternative always comes from the wording. And the problem says this, 17.1. I'm going to read the part that's important here. It says the mean student attitude score for college students is about 50. And the standard deviation is about 15. A researcher in the Philippines is concerned about the declining performance of college graduates on professional licensure and board exams. She suspects The poor attitudes of students are partly responsible for the decline, and the mean for the college seniors who plan to take professional licensures or boards is less than 50. So she's going to do all this, and in her mind, she suspects that the mean is less than 50. She's going to be looking for evidence that the mean is less than 50. That mu is less than 50. If that's 50, that's 50. This is a one-sided alternative. (17.4). Measuring conductivity. State the null and alternative hypothesis for the study of electrical conductivity described in 17.2. Is the alternative one-sided or two-sided? I don't know. We'll have to read it. 17.2. The National Institute of Standards and Technology, the NIST, supplies a standard iron rod whose electrical conductivity is supposed to be exactly 10.1. Is there reason to think that the true conductivity is not 10.1? To find out, NIST measures the conductivity of one rod 6 times. That's a sample with n equal to 6. Repeater measurements of the same thing vary, which is why NIST measures 6 measurements. These measurements are an SRS from the population of all possible measurements. The population distribution has a normal distribution with a mean mu equal to the true conductivity. That's what mu is, right? Mu is the true conductivity of whatever this material is, with a standard deviation sigma equal 0.1. Now, I'm going to back up. They want me to do on 17.4 the null, mu is equal. The alternative, mu. Template. Now I'm going to go back and I'm going to read to you the important part here. The National Institute of Standards and Technology supplies a standard iron rod whose electrical conductivity is supposed to be exactly 10.1. Is there reason to think that the true conductivity is not 10.1? Now that's where the question mark is here. The question mark is always the alternative. What does it mean not 10.1? Does that mean it's greater than 10.1, greater than 10.1, or not equal to 10.1? Not 10.1 means different from 10.1 means not equal to 10.1. If that's 10.1, the null is mu. The true conductivity is equal to 10.1. Okay. 17. Yeah, I'm going to do a couple more if you don't mind. 17.5. The examinations in a large multi-section statistics class are scaled after grading so that the mean score is 75. Mean score is 75. The professor thinks that the students in the 7 a.m. class have trouble paying attention because they are sleepy and suspects that these students have a lower mean score than the class as a whole. I think it's late in the evening and you guys are sleepy and have a hard time paying attention. Just making shit up. The students in the 8 a.m. class this semester can be considered a sample from the population of all students in the course. So the professor compares their mean with the 75, right? All the other students. It says state the null and the alternative. So in 17.5, the null, mu is equal to the alternative, mu. While we're here, you understand that's a two-sided alternative up here. I should have wrote that down for you. Not equals two-sided. Greater than or less than is one-sided. So what's the deal here? What's the professor think here? The professor thinks that the students in the 8 a.m. class have trouble paying attention because they are sleepy and suspects that their score, these students have a lower mean score than the class as a whole. What's it mean to be lower? It means less than the class as a whole. The class as a whole has an average of 75. If that's 75, that's 75. This is a one-sided alternative. Oh, hell, we're doing them. Let's do 17.6. The average income of American women who work full-time and have only a high school degree is $33,230. That sounds like a mu to me. You wonder whether the mean income of female graduates for your local high school who work full-time but only have a high school degree is I always read the important words out loud, is different from the national average. You obtain income information from an SRS of 62 female graduates. They got an X bar of 32,552. What are your null and alternative? 17.6. The null, mu is equal to the alternative, mu. It says the average income of American women who work full-time and have only a high school degree is $33,230. That's your mu. So what do I want to know? I want to know if it's different from the national average. Well, the national average was 33,230. This better be 33,230. That is a two-sided alternative. It didn't say whether they thought one was greater or less than. They just wanted to know if it was different from the national average. 17.7. In planning a study on the number of days in the last 30 the high school students texted while driving sometime during a day, a researcher states the hypothesis as the null is X bar is equal to 15 days. The alternative is X bar is greater than 15 days. What's wrong with that? This is one of the ones, if you do this to me, like you start stating these hypotheses about a population parameter and you start stating them in terms of X bar, me and you got problems. If you see me state anything in terms of X bar here, it's always in terms of your population parameter. It's always in terms of a mu. That's the problem. I don't know what the researcher was doing. You don't state the hypotheses in terms of X bar. They're always stated in terms of mu. Now look, the reason I spent so much time and I worked so many problems here, because in my little head, what separates the test of significance from the other stuff is stating these hypotheses. The calculations we're going to do, they're going to have special language, but we already have done them. Okay? So, I want to get you started on that. So step one is we got to be able to state the hypothesis before you do anything. Okay? And then there is a test statistic. And something called a p-value. Now, the test statistic that's a z-score. That's all. It tells you how many standard deviations away from the mean your X bar is. It's a z-score. It says, a test statistic calculated from the sample data, calculated from your X bar. I'm on page 396, and I'm looking at the little box there. A test statistic calculated from your sample data measures how far the data diverge from what we would expect if the null hypothesis H0 is true. Remember, all this test is done assuming that the null is true, that mu, whatever mu is equal to, that's where that sampling distribution is centered. Your test statistic is measuring how far away from the center that your X bar is going to be. It's a z-score. The z-score tells you how far away you are from your center, what you've assumed to be true, your null hypothesis value. Okay? It says, large values of the statistic shows the data are not consistent with H0. Okay. Large values of a z-score means what? You are a long way away from the center. And I'm going both directions because, look, that's the plus z's, that's the minus z's. You got to get used to me telling you. If I see a z-score of minus 3.21, that's a large z-score. The sign don't mean shit to me other than you went to the left. Right? I mean, I understand that minus 3.123 is negative, but that's still a large z-score, even though it's to the left. Anything to the 3 this way. The further you are out the tail, right, you don't believe the null hypothesis. You believe the alternative. The larger the value of your test statistic, the further you are out the tail, the more evidence against the null hypothesis in favor of the alternative. One more time and then we'll go home. The null hypothesis says mu is equal to something. If you're centered right here, you're going to calculate a z-score. The x bar is going to be given to you, right? So your x bar is either here or it's here. The further out the tail your x bar is, that way or that way, the larger your test statistic, the larger the z-score is going to be. The further away from the center you are, the larger the value of your test statistic, the more evidence we have against the null and in favor of the alternative. So what we're looking for when we do a test, we're looking for large z-scores. We're looking for large values of our test statistic. Why? Now I got evidence for the alternative, which is what we started with. That's what we wanted to know. Okay? What about small values of your test statistic? What about small z-scores? That means you're not very far away from the center, right? That means the data is consistent with H naught, with the mu being whatever it is you're telling me. So it's either going to be large means you're out the tails, you don't believe the null, you believe the alternative, or you're going to be close. Well, the data is consistent with that. Everybody be careful going to the house. We'll see you on Tuesday. We'll pick up with the p-value, and the p-value is just a probability.